Hi everyone, today we're going to look at how to find a missing side length of a right angle triangle using our three primary trig ratios. So up until this point, if we had a missing side length in a right angle triangle, we would use the Pythagorean theorem to find the side that's missing. This required us, though, to have two values for the sides. It required us to have a leg and a hypotenuse, or two legs, in order to be able to use the Pythagorean theorem. In these questions, we don't have the values of two sides. Instead, we have the value of one side and we have an angle measurement. This is when we'll use the trig ratios. So whenever we're going to use the trig ratios, we'll always begin by labeling our triangle. So we'll label our reference angle with theta, and then we'll look across from that for the opposite, across from the right angle for the hypotenuse, and beside or between the reference angle and the right angle for our adjacent. You'll notice in this case there is no value for the adjacent. We know that we're going to use sine anyway because that's what we were told in the question, but this would be the point when we would start to realize that sine is the only ratio that we can use in this case because we have two values related to the opposite and the hypotenuse. So what we'll do is we'll put the reference angle in for the theta, and we'll have sine of 45 is equal to our opposite value will be x, and our hypotenuse value will be 10. Now, at this point, we're going to need to find out the value of the sine of 45. To do this, we'll put 45 into our calculator and then hit the sine button. This will give us a really long value, and we'll have to round it off. I'm going to round it off to 5 or 6 decimal places. That will be equal to x over 10. Now this almost looks like a proportion. We'll put a 1 underneath that decimal and it'll fully look like a proportion, and then we'll be able to cross multiply. So we'll multiply the 1 and the x, and then we'll multiply the 10 and the decimal value. This will give us 1x is equal to 10 multiplied by 0.707107. When we multiply 10 by that decimal, we will get 7.07. There are more numbers on our calculator after that, but we'll round it off and leave it at that. This will be in centimeters, and it will represent the opposite side length within this triangle. So we can add that label to our triangle. We can do a little self-check here also to make sure that that value of 7 is less than the hypotenuse value of 10. It is, and we know that it should be because a leg length is always lower than the length of a hypotenuse. The hypotenuse is always the biggest side inside a triangle. In our second example, we're told that we're going to use the cosine. Let's verify this. We'll put a theta at a reference angle and know that the missing value across from that is our opposite. There isn't a value given here, so that eliminates us using both the sine and the tangent ratios, which require us to have an opposite value. We'll go ahead and label our triangle. The x is the hypotenuse, that's across from the right angle, and the remaining side is the adjacent, again between the right angle and the reference angle. Write out our formula. Cosine is equal to the adjacent divided by the hypotenuse. And we'll substitute the values that we know. So we'll have the cosine of 60 is equal to 15 over x. Now, we'll need to use our calculator to find the cosine of 60. We'll put in 60 in our calculator and hit the cosine button, and this will give us 0.5. So we'll have 0.5 is equal to 15 over x. Again, this almost looks like a proportion. If we just put a 1 underneath that decimal, now we'll have a fraction equals to a fraction, and we can cross multiply. So we'll do 0.5 times x is equal to 1 times 15. That'll leave us with 0.5x is equal to 15. Of course, to get x by itself, we'll need to divide by 0.5. And this will give us x is equal to 15 divided by 0.5, which is 30. This will be 30 meters, and we can verify this by writing that value within our triangle and checking out that our hypotenuse value is in fact bigger than the leg values that were given. So since 30 is bigger than 15, we know we're good to go. Our third example tells us that we're going to use the tangent ratio. The tangent ratio is tan of theta is equal to opposite over adjacent. We'll verify that this is the correct ratio to use by placing our reference angle on our triangle, labeling across from that as the opposite. The hypotenuse is across from the right angle, and it doesn't have any values, either known or unknown, to use. So we know that any of the trig ratios that use the hypotenuse are automatically not going to be possible to be used in this circumstance. Our adjacent value is the one between the right angle and our reference angle. In this case, it's x. So we will have the tan of 50 is equal to 5, which is our opposite, over x, which is our adjacent. We'll use our calculator to find the tan of 50 by plugging in 50 into our calculator and then hitting the tan button. This will give us a number like 1.1917536, which we will then be able to say that is equal to 5 over x. We'll make this look like a proportion by adding a 1 underneath the decimal value, and then we'll cross multiply. Our decimal will be multiplied with x on one side of the equal sign, and 5 will be multiplied by 1 on the other. We will need to divide both sides by our decimal value. This will leave us with x on one side, and on the other side we'll have 5 divided by our big long decimal. When we divide this in our calculator, top number divided by bottom number, we'll get x is approximately equal to 4.2, and this is in meters. So we have two leg lengths of this triangle, one at 5 and one at 4.2. We don't know the hypotenuse, but we'll be expecting that it'll be greater than either of those values. So that is how you solve a trig ratio in order to find the missing side length within a right angle triangle.